Hello, today we're going to cover College Algebra 2.4 and everyone's favorite word problems. So we start off with systems of equations. Now there's a few different ways that you can solve a system of equation. You've probably seen these once at somewhere in your life. Substitution, elimination, and then we could solve it graphically, or we could use our handy dandy calculator and use matrices. So keep your calculator handy and I will show you the easiest way. So real quick, just to appreciate its easiness, let's cover this problem here in a couple of different ways. So substitution is generally kind of the go-to. Usually when people see it, it makes the most sense. They kind of go for it. So to solve this problem with substitution, I would take either one of the two equations and solve it for one variable. So for example, if I chose substitution and chose the top equation and chose the top equation to be solved for x, then I would add y to both sides to see that the x equals positive y plus 5. Because remember, adding it to the other side would cancel it on the left, therefore making it be a positive y plus 5 on the right. I would then substitute this equation in for the variable x of the second equation. It's saying that x and the value of y plus 5 more are interchangeable. So the value of x, the mystery number x, is 5 higher than whatever the mystery number y is. So we're going to use that and replace this x right here. So I'm going to rewrite this equation to x plus y equals 1. But in place of the variable x, I'm going to substitute y plus 5. Now, just like any other problem, I'm going to distribute and solve it for the variable y. This, of course, would give me 2y plus 10 plus this y over here. Remember to combine your like terms. Don't try to subtract y both from the same side. And then I move my numbers. And last I divide to get y all by himself. Oops, sorry. Finally, to see that y equals negative 3. Always watch those signs. So this is only half of our solution. If I needed the system of equations, I need both of the points, x and y, both of the values, to see how I could find this solution. What point on the graph would make this true? So I continue the problem by resubstituting this known value of y now for either one of these two, because they should both meet in the same point. So if I happen to choose the top one, x minus y equals 5, and now replace that value of y with this value I've discovered, that y should be equal to negative 3 to make this work out, then x minus a minus 3 equals 5. Remember that double negative becomes a positive, so that really means that x plus 3 is 5. Which, if you subtract the 3 from both sides, means that the x would need to be a positive 2. So I rushed through this just a little bit because this isn't really going to be the way I recommend you solve these. So don't worry if you're not quite on the same page just yet. Now reworking the same problem, starting back over, pretending that I don't know the solution now is 2 comma negative 3. Let's think about the other way to solve it with the elimination. So if I copy the problem over, let me just rewrite it. Okay. The x minus y and the 2x plus y. Another way to solve this system of equations is to eliminate one of the variables. Now in this problem, it's actually set up really well for an elimination because this one has a negative y and this one has a positive y. But just so you can see that even if it wasn't that easy, it would still work out. I'm going to do it the harder way. Now this top equation has one positive x. The bottom one has 2 positive x's. If I wanted to eliminate one of the x's and make them kind of match, usually we use integers instead of fractions. So I would multiply the top equation left and right by the value -2. That's going to change the top equation into -2x plus 2y equals -10. So notice that I've distributed this -2 to each one of these three members. This one, and this one. I'm going to copy down the bottom equation exactly the same as it was. And now I'm going to eliminate those x's by adding the equations as a whole. So just like if I'd been combining like terms. So -2x and +2x cancel, just like I wanted them to. +2y plus another y would make it 3y. And -10 plus 1 makes -9. Kind of looks familiar, right? So in that last step, when I divide by 3, we do end up with the same answer as before, which makes sense. We were expecting it. So this would give me the value that y, of course, is -3, which then, just like the last one, we would usually do a substitution at that point, sub it back into either one of those two to find the given corresponding x of 2. So these are two methods. Another method is graphing, where I would just literally graph the two lines. Now that one is a little bit sneaky because if we're using our TI calculators, we have to get it in y equals form, which means I would need to kind of manipulate this equation to solve it for y, then plug it into the calculator. And then it would really only be helpful if the answer was integers like this right here. So if I had an answer of like 2.78942, that would be really hard to see visually on the calculator. And even if I use some of the calculator features, I'm still going to have a limitation to the rounding that it does. So that's why I never even really go to the graphing. It's just pretty limited. It's the least cool. So these are the more precise methods. Substitution, like I said, tends to be people's favorite, but the elimination can work out really nicely, especially in this case where, like I said, we were already set up to have one variable be eliminated. Now in these last two right here, we're going to go one more time, kind of over these methods. So this one, if I wanted to do that substitution again, I could solve it pretty easily for x by adding the 3y to both sides. So I would see that the corresponding equation would be that x equals 3y plus 1. Again, he's positive because I'd have to add him to the other side. I would then substitute that in place of the x of the second one. So notice I just put a big kind of bubble right there where the x was. And then I'm going to fill in that bubble with his substitution, 3y plus 1. And then work it out like normal. Now this one's going to do something funny, so keep an eye on it. This right here is one of the few rare special cases. Most of the time, probably 97% of the time, they work out like this. Now this happens because graphically, these would have two completely different lines that would cross each other in one single point x, y. So that the only point that would be on both of those lines is the point 2, -3. Now this one, as we work it out, I see that weird thing happen where these cancel. It's kind of like the problem we saw in the earlier chapter where we got the no solution. It's kind of like a no solution. -2, of course, does not equal 5. So this would be this special case of parallel lines. Parallel lines are inconsistent. Consistent means we got an answer. There was a point where both of the conditions were fulfilled. This one would not have any point that could make this line and this line work out. There is no point xy that would be on both this top line and this bottom line. So this one is inconsistent. Now here's the other one special case. And again, remember it is a special case. So most of the time it's like this guy. So if I wanted to practice my elimination again, like this where I was making something eliminate, I see, okay, here's a +4, here's a +2. So let's again multiply by a -2, because that will make these match. That would make the top equation be -4x minus 6y equals -12. And then just rewriting the bottom equation, we start to see something fishy's going on because I was trying to make the x's cancel. I did that, but unlike this one over here, the y's also canceled. So basically I had nothing left on the left. Well, on the right, let's see if it's inconsistent like the last one, but negative 12 plus 12 is also 0, the same 0. So this is the other special case. This one is the dependent case. This occurs in the 2D world, Cartesian coordinates, when I actually had the same line twice. So they had some sort of different multiplier to make them look different, but I actually was dealing with the same exact set of numbers, x, y, the same ordered pairs. So they formed the same line. So they are consistent. They have a solution. In fact, they have infinite solutions, but they are dependent on each other because one is completely identical to the other. So these other two, we had two independent lines. They were different. They had points that were apart from each other. This one was inconsistent because they never crossed to find a point xy on both lines. This one was dependent because it was the exact same line both times. Inconsistent for basically a no solution, dependent for those all real numbers kind of case, to compare it to our earlier lesson. So all of that to say, we really don't need to do any of this because once we take things up a degree, things get infinitely more complicated. Not really infinitely, but a lot. Because these 2D cases, we only had one solution, no solutions, or infinite solutions. If you add just one more dimension, things get crazy. We could have the one solution, which is our favorite, where the 3D planes all connected in one single nice pretty dot. But any of these other things could have happened. They could have kind of formed this 3D triangle where any two planes would cross each other, but there was never a point where all three came together. They could have all been completely parallel where nobody crossed anybody. It could have been that same kind of line on top of itself where it was one single plane just with different multiples. Or it could be kind of like a book spread out like this where all three planes met together with infinitely many solutions on a line. So because of that, lots going on here, and the fact that you would have to solve it with substitution or elimination in all of these stages, this is actually a very precise way to solve it. This is about as short and neat as you could do it. You can see it's pretty complex. I recommend your calculator. So grabbing your calculator, let's learn how to solve these problems without any of this. We're going to use the Matrices function on the calculator. It's not a special program. You don't have to get the programs from me. It's just automatically built into that TI 83 or 84 calculator. So the first thing we need to do is to learn how to talk to our calculator. It's going to ask us about the order of the matrix. Now this always seems a little bit backwards to me because I think x, y on the Cartesian coordinate, the order of the matrix is a little bit backwards. So we do rows, columns. So reverse out of alphabetical order, row by column. So this one would have an order of 4 by 2, 4 rows, 2 columns. This one would have an order of 2 by 5, 2 rows, 5 columns. So like I said, a little bit backwards, reverse of alphabetical order, and not left, right, up, down like you would with the ordered pair. So in this one right here, if I wanted to communicate with my calculator and put it in, I would put it in as a 3 by 4 matrix. Okay, now it would need me to fill in all of these positions, even the ones that were blank. So I do that by writing it in as just the coefficients, no letters at all. So remember the ninja numbers, the coefficient of this x right here would just be the understood 1 in front of it. There is 1x. There are negative 8 y's, positive 6 z's, and then that is equal to negative 6. So again, notice there are no x's and y's. Because of that, it's incredibly important to be neat and clear. So since I put it as x, y, z, I have to be consistent. The next line has to be x, y, z, or the whole thing falls apart. Next, I've got 8 x's, minus 5y's and another 6z's, watch those signs, equal to 4. This is the one I mentioned. We have to be consistent. So right here, this is the x's. In the third line, there are 0 x's. I put a 0 as that placeholder. 7y's, negative 1z's, be careful, equal to negative 5. Now for our human brains only, just to kind of understand, we put this straight line right here for human eyes to indicate that these were the variables, this was the equal sign, and this was the solution. In the calculator, we won't put that line. It's just for humans. Okay, so that's a human line for our human eyes. So right there, don't put it in the calculator. So now let's interpret, because once we tell it what we need in computer speak, it's going to give us the answer in computer speak. So let's go see if we can figure out what that means. So if it told us this, and remember, it would never show us this line. It's just for us. This is because a human made this for us. It would tell me they were actually saying that there was 1x, positive 5y's, negative 7z's, equal to 6. So be careful, don't write 1x, 5y, negative 7z. There's pluses and minuses between each of these terms. This one, that 0 is the placeholder. So this one has 0 x's. It starts in with the 7y's. I could put 0x, but it's not fully simplified. So let's just start with the y's. The last line, I've got 7 x's, but then it skips the y's and goes straight to the z's. So if I wanted to put this right here, the system of equations, into my calculator, into the matrices form, I would use those coefficients, 2, 4, negative 6, negative 2, positive 2, and 12. Remember, I'm not going to put the line because that's just for us, into my matrix. All right, here we go. Here's the steps. It seems like a lot the first time, but it's really in 3 stages. So just kind of keep it in stages in your mind. So I'm going to go into the matrix. So I use my second button, and then right down here, this one says matrix in blue. So I do my second matrix. Okay, then it gives me all of the matrices option. In my first stage, I'm going to arrow over to edit. First time I'm going to edit a matrix. When I hit enter, it gives me the option for whatever order of matrix I want. This one has 2 rows by 3 columns. So I do 2, enter, 3, enter. And then you should see kind of a setup for a 2 by 3 matrix. Hit enter one more time, and you can start entering in the values. So I hit 2, enter, 4, enter, negative 6, enter, making sure to use the little negative down here, not the one on the side. And when I hit enter, after that negative 6, it automatically takes me to the next line. So I go negative 2, enter, 2, enter, 12, enter. And it should look just like you have on the screen. If it doesn't, go back and double check that. Now here's the most important part. After you hit the 12, enter, make sure that you do a second quit. I forget this step half the time and it messes me up. So right here, before you go to the next step, you have to get off of the screen and go back to your regular home screen. So don't forget to second quit. Okay, if you ever forget it, it's super obvious and you can just go back a step. Next, we're going to go into the matrix again for the second time. Okay, so all of that was step 1. This is step 2, second matrix. This time we go to math. Arrow over to that second option. Don't hit enter yet. It has lots of different math things we can use, but I need a certain one. So I scroll down, keep going, keep going. We want the one that is RREF. So be careful, there is an REF, but we want RREF. So not RUF, we want RREF. So make sure you're doing RREF right here. So it stands for row reduced echelon form, but don't worry, I'm not going to have a vocab quiz. RREF. Okay, so after you select that It should put it back on your blank home screen. So like I said, if you forgot to second quit, you'd see it in the matrix and you know something was up. So he's on your blank home screen waiting for you to do the third and final step. So one last time, second matrix. And then if you put it into matrix A, you want it to re-roof matrix A. So I hit enter, enter. And there it is. So first time we put the matrix in, we did edit. Second time we selected re-roof. And then third time we told it to re-roof our matrix. 3 stages. So it told us our answer in weird calculator speak, matrices form. But remember, just like we did up here, we can interpret this. So this was really saying that we had 1x and 0 y's equal to -5, 0 x's and 1 y equal to 1. So that means this was really x is -5. And this one was really y is 1. And that's our answer. We're all done. Now it seems like a lot the first time, but it's way better than all of this, I promise. So let's try it with a bigger one. Here we go. Change colors. Let's put it in our matrix form. 1x, -2 y's, 3 z's equal to 11. 4x, 2y, -3z equal to 4. Always watch those signs. 3x, 3y, -1z, and 4. No zeros, no placeholders this time. Here we go on our calculator. Second matrix edit. This time it's a 3 by 4. 3 rows, 4 columns. Enter in all those numbers, making sure to use the little negative on the bottom. And then after you get in that final 4, don't forget to second quit. Don't forget to second quit. Okay, now we go second matrix for the second time. Over to math, don't hit enter yet. Scroll down to re-roof. Last time, second matrix, enter, enter, and there it is. Row reduced echelon form gives us the answer 100, 010, 001, and 3, -1, 2. So that means the answer to all of this was really the point on the 3D graph with an x of 3, a y of -1, and a z of 2. Sorry, clean that up a little bit. At that point, all 3 of these planes would meet. X, y, and z. So we can try it one more time right here. With this one, you will see that you get an answer that is a fraction, but that's okay, because as always, you can do that math, enter, enter. So this one does have a placeholder, so just be careful when you're entering it into the matrix that you do it as the 2, -1, 4, 3, -3, 1, -2, -10, -6, 3, 0. The y's were missing in that last row, and 7. When you give that a try, you should get the solution where your x is 3, your y is 7, and your z is -1/2. So it makes everything much easier